Hello, welcome to the last part of the module, which is the Lagrange Multiplier Method. Now, we have already done Lagrange's method for a maximum and minimum. We use the multiplier method for a constrained maximum and minimum, that is, there's some condition which limits the area. So, how to solve it? Let's start with step 1. We must identify a function f of x, y, z, and we call it u, where the relation g of x, y, z exists, where your constraint method can be written in this form, where you have to find the extrema of this function with respect to this condition. So, there is a condition represented by g of x, y, z. Then we construct the Lagrangian function, which is in L in terms of x, y, z and lambda, which we can expand in this form here. F of x, y, z plus lambda times g of x, y, z, where lambda is Lagrange's multiplier. Then we must obtain the equations. The equations we can do by taking the first derivative with respect to x, y, z and lambda, and then we obtain the values of x, y and z by solving these equations. So now our answer will be of the form a, b, c. So it's coordinates x, y and z, which have the values a, b and c, which is a stationary point which satisfies the maxima of this with respect to the relation g of x, y, z. Take an example. Temperature T at any point x, y, z in space is given as T equals 400 x, y, z square. This is my given f of x, y, z, because this is the thing where I have to find the maxima. This is the condition with respect to I have to find the maxima or minima. Find the highest temp on the surface of unit sphere of equation this. So this is equation of a unit sphere. Now this is at any point in space. This is on the surface of a unit sphere. My condition is that I have to find the highest temperature on this surface of this. So only the points on the surface of this counts, making this the limiting condition. So f of x, y, z is 400 x, y, z square. G of x, y, z is x square plus y square plus z square minus 1. Why? Because I want it to be g of x, y, z equals 0. By Lagrangian multiplier method, L of x, y, z is to lambda can be written as f of x, y, z plus lambda times g of x, y, z. F of x, y, z I have over here, g of x, y, z I have over here, I substitute. Then I take a derivative with respect to x, a derivative with respect to y and a derivative with respect to z, and I equate all to 0 because that's my step over here. That is step number 3, as you can see over here. Step 3, take a derivative and equate it to 0. So I take a derivative with respect to x, y and z, and then I get everything in terms of lambda. So I get lambda equals this, and lambda equals this, 3 equations. Now all 3 are equal to lambda. I can call it a, b and c over here. So then I can equate a and b, and on equating a and b I get the relation y square is x square, that is y is x. On taking b and c I get the relation z square is 2y square, so z square is 2x square. Now I got all 3 variables in terms of one variable. I can convert y as x, and I can convert z to root 2 of x. But that isn't necessary. As you have x square, y square, z square, just substitute as x, everything in x square, you'll get a value for x. Now y equals x, so that's how you get y equals x is plus minus half. And then you have 2x square equals z square, so then z you can write it as plus minus 1 by root 2. Now this is the point on the surface of the sphere where the maximum temperature is obtained. So this is your stationary point on the surface, and these are the values a, b and c. The temperature obtained is given by 400 x, y, z square, which is what we do over here. We get the value as 50 degrees Celsius. Moving on to the next question, you have find dimension of rectangular box of maximum capacity whose surface area is given when the box is open and the box is closed. So you have to find the dimension of rectangular box of maximum capacity, and you have to consider the surface area for 2 cases, when the box is open and when the box is closed. So when it is open, the surface area will be of 5 sides. So that we take it as length into breadth plus twice length into height plus twice breadth into height. The volume is going to be constant as length, breadth, height. If we call x as the length, y as the breadth and z as the height, we say f of xyz equals v, that's my volume, equals xyz. My limiting condition over here is going to be my surface area, which is xy plus 2xz plus 2yz. So I've taken 2 out common. Again, following the same steps, we get L in terms of f of xyz plus lambda g of xyz, take a first derivative, and then you can continue with two methods. I'll show the second method in the second part. Over here, this is the same method as your first one, where you equate everything, and then on equating any two terms, you will get a relation. Over here, we get a relation between y and x. Over here, we get a relation between y and z, and that's how we use it. So we get x equals y equals 2z. Now, now for the closed box case, the only thing changing is the surface area, which becomes twice of xy plus yz plus zx. The volume remains the same. Following the same initial steps, rather than taking dou L by dou x, I have written it as dou S by dou x. So before we take the Lagrange multiplier, we are taking an individual derivative of the surface area. So we have got twice y plus z, twice x plus z, twice x plus y. Now taking it in the form of Lagrange multiplier, where this is going to be a derivative of f of x comma y comma z, this is derivative of g of x comma y comma z. That's what we have done. Derivative with respect to x is y z, and from here we know it's 2y plus z, lambda comes in, so 2 lambda y plus z. Like this, you'll get 3 equations. Now, rather than equating them with respect to lambda, you try to simplify it simultaneously. So we multiply 1 with x. Let's see what 1 is. 1 is here. So we get xyz plus twice lambda xy plus z. Multiply 2 with y, xyz plus twice lambda y x plus z. And then you subtract the 2. On subtracting, you get twice z, x minus y times lambda. And the same way, you get x equals y. Moving on, you can do the same thing over here, where it's multiplying 2 with y and 3 with z. So 2 we know from here is this equation, is this one here, this equation, and 3 over here. So you're getting xyz plus twice lambda y x plus z, xyz plus twice lambda z x plus y, and then you subtract the 2. So on subtracting, we get this result, 2x y minus z times lambda. From here we get y equals z. So from 4 and 5, we can say x equals y equals z, that is length equals breadth equals height. So now whatever they give us, the volume is 32 centimeter cube. Find the length, breadth and height when the box is open. So since the volume is given and we have a relation between length, breadth and height over here, x is y is 2z, then just substitute everything here. We'll get x square into x into 2x. Yeah, sorry, I made a mistake. We take x, y, z equals 32, but x equals y equals 2z. So then we take 2z into 2z into z. 4z cube is 32. Like this, we get the value of z equals 2 centimeters. And then we can continue saying y equals 2z, which is x as well. So that we get as 4 centimeters.